Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I'd like to finish going through Chapter 5.1 examples of linear transformations. If you could turn to our guided lecture notes, I'd like to start on page 6 of our notes. In our previous examples, we were working on linear transformations from Rn to Rm. I'd like to look at examples now where our linear transformations are into different vector spaces. And depending on how the transformation is done, sometimes we don't represent it using the letter t. So for this linear transformation, we're calling it d. And d is a transformation that takes functions that have continuous first derivatives on the interval 0 to 1 to continuous functions on the interval 0 to 1. If you don't remember some of this notation, you might want to refer back to chapter 3.5 when we introduced prominent vector spaces. But again, your domain are functions that have continuous first derivatives on the interval 0 to 1 into your codomain continuous functions on the interval 0 to 1. And the way that we do this transformation is by the function. So this tells us how we perform this transformation. By taking 2 times your given function, or 2 times your function's derivative plus your original function. So here you'll notice that they're using d because we're talking about derivatives. It's still going to be a transformation. We could have called it t if we liked, but they're trying to be specific with our examples and maybe use d because we're taking derivatives. Here, we want to show t is linear or find a property that it fails. Again, I like going in the same order every time I do these, so I will always start with checking the property of scalar multiplication first. And so what we're trying to show here is that d times a scaled version of some function in our domain is going to equal a scaled version of d times a function in our domain. So now let's apply d to what this input is. So notice that what d does is it takes some function, it multiplies its derivative by 2, and then adds it to the original function. But here our input is not just f, it's cf. So I guess what I'm trying to get you to see is that this is going to look like 2 times cf prime plus the original input, cf. From calculus, we know that the derivative of a constant times a function is just a constant times the derivative of a function. And if we want to, we can probably eliminate all these parentheses and just write this as 2cf prime plus cf. Now we would like to see, is this equal to the right side? So here we're going to look at a scalar times d of f, but d of f is going to be 2 times the first derivative of that function plus the function. Of course, if we distribute the c, we'll get 2 cf prime plus cf. So notice that the left side is equal to the right side, and we have shown that D does preserve scalar multiplication. So now let's move on to vector addition. Here we want to show that D of the sum of two functions in our domain. So maybe let's let f and g be the functions in our domain. We want to show that this is equal to d of f plus d of g, where f and g will be elements of our domain, so they'll have a continuous derivative on the interval 0 to 1. Now we can't do anything with f and g, we can't add them together since we don't know what they are, so let's apply d to this sum. Remember what d does. It takes 2 times its derivative, the input's derivative, plus the original input. So this will look like 2 times the derivative of f plus g plus f plus g. Of course, from what we know from calculus, that the derivative of the sum of two functions is really just the sum of its derivatives. And if we want to, we could probably distribute this 2 and write this as 2f prime 2g prime plus f plus g. And there's probably a variety of other ways I could rewrite this, but I'm going to stop there. And now what we would like to do is verify that this is equal to the right-hand side. So first we'll apply d to our function f, which is going to be 2 f prime. Oh, let me change my parentheses here. I don't need these. D of f is going to be 2f prime plus f, while d of g is going to be 2g prime plus g. And while we can get rid of these brackets if we want, they're just used for grouping that I was using to isolate what each of these looks like. I think we would like to identify that both of these are the same. They're written in a different order, but these are the same. They're equal. This allows us to say that this transformation preserved scalar multiplication, it preserved vector addition, so that we can say D is a linear transformation both vector addition and scalar multiplication. Okay, let's look at another type of example. Consider the mapping I that maps continuous functions on the interval a to b to real numbers defined by I of some function is the definite integral of that function on the interval a to b. So remember, with all these linear transformations, we have to be given a domain, a codomain, and a function that tells us how to go from one vector space to another. So notice that we're given a function, but this definite integral is always going to produce a real number. So it'll always produce an element of your codomain. Here I want to show t is linear or find a property that it fails. So let's start again with scalar multiplication. Here I want to show that I times some scaled version of a function from our domain is going to equal to c times I of some function in our domain. I'll start with the left-hand side. When we look at the integral of a constant times a function that's continuous on the interval a to b, this will be equal to the definite integral from a to b of c times f of t dt. However, from calculus we know that the integral of a constant times a function is the same thing as a constant times the integral of a function. Notice by definition this is equal to c times I of f, which is the same thing as the right hand side. These are the same. And so that we can verify I does preserve the operation of scalar multiplication. Now let's look at vector addition. Here we would like to show that I of the sum of two functions in our domain will equal to the sum of I of each of these functions individually. Now remember what I does. I takes some input and does the definite integral of that input. So let's do the definite integral of this input. So this will be the definite integral from a to b of f of t plus g of t dt. However, from calculus, recall that the definite integral of the sum of two functions is going to be the sum of the definite integrals. However, by definition, this is I of f. And the second integral is I of g. So notice that this again equals the right-hand side. These are the same. And so we have shown that I does preserve vector addition. So our conclusion, because I preserves vector addition and scalar multiplication, I is a linear transformation. Now, I've done several examples, but there'll be even more in your homework for you to work on. I hope this is helpful. Now I'd like to move on to a different type of transformation. Matrix transformations. Every linear transformation T that maps Rn into Rm can be defined by an m by n matrix A, and the matrix multiplication will complete the transformation. Many of these linear transformations can also have a geometric interpretation. So T going from Rn to Rm. So here we're going to start with an element in our domain, Rn. So let's let V be an element of Rn. We apply T to V by doing the matrix multiplication AV. And what we're going to get back is a vector B, where B is in Rm. This will be our codomain. So the matrix multiplication is going to do our transformation for us. Let's look at an example. Consider a transformation that shears the plane in R2. The term shear comes from the shearing stress that dislocates different layers. So notice that depending on how high up your layer is, you have more shear. This is something that can be seen in many applications, such as snow avalanches, or maybe moving water. Imagine water that's moving down some kind of a surface. The water that's at the bottom touching the surface may move slower than the water that's at the top. Imagine a river. The river flows faster at the top than it does at the bottom. So there's lots of applications where we might see some kind of a shearing stress. The shearing of a plane in R2 can be defined by the mapping T going R2 to R2, where T of some element in your domain is transformed by this matrix multiplication. To get an idea how this works, let's consider a couple of examples. Let's maybe look at T of 1, 1. I pulled that out of nowhere just as an example to start. To find how the point 1, 1 is transformed, we'll multiply 1, 1 by this matrix. And now recall from chapter 3, when we're doing matrix multiplications, one way to do it is to look at the first row times this column, adding your products as you go. So 1 times 1 plus 1 times 1, I think we get the first element here is going to be 2, and our second element will be 0 plus 1, so 2, 1. Maybe we could also look at T of 1, 2. T of 1, 2, we can find out how this is transformed by multiplying by this matrix. And I think when you do this matrix multiplication, you get 1 plus 2 is 3 plus 2. And for giggles, let's just do one more. This is fun. Let's look at what T does to the 0 vector. Remember from our previous examples, a linear transformation must always send the 0 vector to the 0 vector. But notice that any matrix times 0 is still going to be 0. Now to visualize this transformation, let's draw a little coordinate system here. We'll label this Y and X. So from the bottom, the first one we did was the origin, 0, 0. And 0, 0 did not move under this transformation. 0, 0 stays at 0, 0. 1, 1 was 1 over, 1 up. It was this point here. 1, 1 got shifted to the point 2, 1. So it experienced a shear of 1 unit to the right. The other point that we did 1, 2, this point translated from 1, 2 to 3, 2. Or in other words, it experienced a shear that moved it 2 units to the right. So the first one experienced no shear, 1 shear, 2 shear. Maybe I can label this your shear value of 0, your shear of 1, your shear of 2. So notice that the higher your y value, the further up from the horizontal plane, x equals 0, axis, you experienced more shear, like you might expect with water moving in a river. So that's what this linear transformation looks like, or this transformation looks like. Maybe I shouldn't say it's linear till we first verify it's linear. So let's verify this is a linear transformation by first looking at the property of scalar multiplication. Again, with these properties, we want to verify that t of some scaled version of an element in our domain is going to be equal to a scaled version of t of that element in our domain. And let's grab a typical element in our domain. A typical element is going to be an ordered pair. So we'll look at t of c times some element in our domain, which would be an ordered pair xy. Of course, when we scale a vector, we'll scale each component. And now to apply t to this vector, we'll multiply by the matrix 1, 1, 0, 1. And when I multiply this matrix times this vector, again, the way I do this is multiply your row that you're working on times this column. So it'll be 1 times cx plus 1 times cy. And I think what we get is cx plus cy. Your second element, your second row is going to be 0 times cx, 1 times cy. That's just cy. And now we want to verify, is this equal to the right hand side? So now we'll look at c times t of some vector xy, which will be c times the matrix 1, 1, 0, 1 times our typical element xy. Now again, when you do this matrix multiplication, we're looking at what happens when you multiply the row that you're working on times the column and adding up those products as you go. I think we'll get as our first component x plus y. Our second component will just be y. And if we distribute our scalar, we'll get cx plus cy and cy. Notice that these are the same, so that we can say t does preserve scalar multiplication. We still need to work on vector addition. So now we want to show that t of the sum of two vectors will be the same thing as the sum of t of each of these vectors individually. And let's start by grabbing what some typical elements might look like. So maybe vector u might look like x1, y1, while vector v might look like an x2, y2. While on the right hand side we want to look at, well, let's just do one side at a time. Just make this easier. Let's look at just the left side first. So if this is the left side, maybe the first thing we'd want to do is add the two vectors together to have x1 plus x2, y1 plus y2. And now we'll apply t to this vector, which will be multiplying by this matrix. And again, when you multiply this matrix times this vector, the way I'm going to do it is I'll multiply the row that I'm working on times this column. I think what I should get here is one times x1 plus x2 plus 1 times y1 plus y2. Our second component is going to be 0 times x1 plus x2, and then 1 times y1 plus y2. Well, I'm sure I could rewrite that in some way. I think I'm going to stop there and look at the right side and see what we get. Now remember, for the right side, we want to apply t to each vector individually. So here I'm going to look at t of x1, y1 and add this to t of x2, y2. Where each of these transformations will be accomplished by the matrix multiplication I believe if I do these matrix multiplications, again, your first row times your column would be x1 plus y1. Your second row times that column would just be y1. 1 times x2, y2, I think it's going to be x2 plus y2 and y2. And if you add these two vectors by adding their corresponding components, then I think we should know that even though these are written differently, I believe these, the left-hand side and the right-hand side, are both the same. this verifies that T preserves vector addition. So maybe we can say because T preserves scalar multiplication and vector addition, T is a linear transformation. Okay, let's move on. This leads us to talk about a standard matrix for a linear transformation. If you're given a transformation T mapping Rn to Rm, then there's a standard matrix associated with that linear transformation that does the transformation for you. The way we can find this matrix of transformation is to see what T does to each of your standard basis vectors. So if E1 is your first basis vector and E2 is your second basis vector, you apply T to each basis vector and then create a matrix from those values. This will create a matrix that does the transformation T for you. And because matrices are inherently linear, this will verify also that our transformation is a linear transformation. Let's work on an example so you can see how this works. Here we want to find a matrix of transformation for the linear transformation mapping R2 to R2, defined by T of xy is x negative y. And then identify what is the geometric interpretation of this transformation. So here what we want to do is we want to find a matrix A such that T of some ordered pair from R2 will be equal to A times that ordered pair, and that after multiplying by A, what we get back is x negative y. So we want to find a matrix that does this linear transformation. Notice that when we write this, what the dimension of A must be. And to identify, notice that this vector xy that we're multiplying here, this is a 2 by 1 matrix. And what we get back is a 2 by 1 matrix, 2 rows, 1 column. So that for this matrix multiplication to work, A has to be a 2 by 2 matrix. Because then recall from chapter 3, the inner dimensions agree. This allows us to do the matrix multiplication, where the outer dimensions, that tells you the size of your product, are 2 by 1. So A we should predict is going to be a 2 by 2 matrix. But to see how to create A, let's look at our first standard basis vector E1 for R2. In R2, our standard basis vector, the first one is 1, 0. And our second standard basis vector E2 is 0, 1. So we want to see what does T do to these two basis vectors. So let's apply T to the vector 1, 0 first. X component is 1, Y component is 0. We plug that in. I think we're going to get still 1, 0. It doesn't change. When you apply t to the vector 0, 1, remember, the X component stays the same, but you negated your Y component, so this is going to be 0, negative 1. Putting these together, this tells us that our matrix A has to look like 1, 0, 0, negative 1. So this is your matrix of transformation. To see that it works and to get an interpretation of this transformation, let's look at some examples. Let's consider what t does to the ordered pair 1, 2. And while we could just use the given transformation, I want to use the matrix. So to apply t to 1, 2 is equivalent to doing this matrix multiplication. And if you do this matrix multiplication, I think you should get 1, negative 2. Similarly, let's look at the transformation to the ordered pair 3, negative 2. And if you do this matrix multiplication, I think what you should get is 3, positive 2. I think graphically what we should see here let's make a little coordinate system that we can plot some points on, is that we started with the ordered pair 1, 2, so 1 in the x direction, 2 in the y direction. Here's our starting point 1, 2. However, after the transformation, it has got moved to the ordered pair 1, negative 2. So this point got moved to this point. Similarly, 3, negative 2. We started here. After this transformation, this point got moved to the ordered pair 3, 2. This point got moved to this point. I think what we want to see with this is that the transformation t reflects points around the x-axis. Anything that was above the x-axis will get transferred below, reflected below. Anything that's below the x-axis will get reflected above the x-axis. So that's our geometric interpretation. Okay, let's look at another example. Here we're asked to find the matrix of transformation for the linear transformation t mapping R2 into R3 defined by this function. And this is where I'd like to pause for a moment and give you the opportunity to find this matrix A of transformation on your own. So if you could pause the video and find your matrix of transformation. Afterwards, come back and we'll see if we agree. I'll see you in a moment. Okay, let's see how we did. Again, we want to find a matrix A that performs this transformation. put it another way, we want to find a matrix that takes an ordered pair xy, that when you multiply by this matrix, it takes xy and it gives you back x minus y, x plus y, and 2x. So we're trying to go from an element in our domain, an ordered pair, and find an element in our codomain, an ordered triple, that does this. And again, the way we do this is we look at what happens to each of our standard basis vectors. So here we'll take our first standard basis vector, E1, which for R2 looks like 1, 0. We'll take our second standard basis vector, E2, 0, 1. When you apply T to the ordered pair 1, 0, again, x is 1, y is 0, so plug in 1 for x and 0 for y. I think we get 1, 1, 2. For our second standard basis vector, 0, 1, I think we get -1, 1, 0. This allows us to say that our matrix of transformation has to be the matrix 1, 1, 2, -1, 1, and 0. This is our matrix of transformation that does the same thing as using the given function. Okay, let's look at one more example. Consider the transformation that maps R2 onto R2 defined by this function. Here we're asked just to compute the image of a vector under T. And then in part B of this question, we want to find a vector, if any, that gets mapped onto W. Let's start with part A. I actually think there's two ways you could do part A. First way, you could literally just take your given function and apply that function to the input 1, 2. So if you take the ordered pair 1, 2 and plug it in, x is 1, y is 2, I think we get back the ordered pair 1, 5. This is the image. This is what 1, 2 looks like. 1, 2 gets transformed to the vector 1, 5. That's the image. However, an alternative way to do this is to find your matrix of transformation. Let's find A. And to find A, I want to see what T does to each of our standard basis vectors. So let's first look at what T does to 1, 0. When you plug 1, 0 into our transformation, I think we get back the vector 1, 1. We'll apply our transformation to our second standard basis vector. And if x is 0 and y is 1, I think we get 0, 2. This tells us that our matrix of transformation A has to be the matrix 1, 1, 0, 2. So an alternative to finding the image would be to look at T of Let's see, we're looking at 1, 2. T of 1, 2 can be found by looking at the matrix times 1, 2. And I believe if you do this matrix multiplication, you get 1 as your first component, 5 as your second component. And so it should be, of course, that these are equal. Just different methods of finding the image. Now let's find a vector, if any, that gets mapped onto 2, 8. So specifically, what we're trying to do is find a vector v in your domain that gets mapped onto the vector 2, 8. Like, what vector gets mapped onto this one? Or to put it another way, we want to find t of some vector xy, and I like using the matrix multiplication for this, that when you multiply by this transformation matrix, what we get back is the vector 2, 8. And our question is, what is this vector v? What is this vector v here, this x comma y? Notice that the way I've written it, this really looks like a matrix equation. Ax equals b. And so I'm going to solve this matrix equation using methods that we learned in chapter 3. I'm going to start by writing our augmented matrix. So 1, 1, 0, 2. Again, I like separating my right-hand side with a dashed line. This is my stylistic choice. And I could use a matrix calculator, but I believe for this matrix, since it's so small, it'll be easier to do this by hand. With this as our pivot position, we want to make what's below that pivot turn into 0. So I'm going to go negative row 1 plus row 2. When doing this transformation, the first row of our matrix does not change. Negative of 1, add that to 1 is 0. Negative of 0 added to 2 is still 2. Negative of 2 added to 2 is 6. Now we want to create a pivot in this second position. And to accomplish that, I'm going to multiply the second row by 1/2. When multiplying the second row by 1/2, the first row of our matrix is not going to change. But we multiply by 1/2, this will be 0, this will be 1, and this will be 3. Notice that because we have 2 pivot positions and no free variables, that this is going to give us one unique solution. So here our solution, our vector x comma y that we were looking for, has to be the vector 2, 3. 2, 3 is the vector that gets mapped on to 2, 8. Okay, I think this is going to be enough examples for you to get everything done in your homework for chapter 5.1. So I'm going to stop here. I hope this is helpful, and I'll see you in our next video.